Roxanne. Oh. Mm. Hi, Roxanne and Jennifer. Roxanne, hopefully you didn't hear me singing. As soon as your name popped up, I went into Roxanne. I just didn't remember there being a Roxanne in my class, and I can't see that name without singing it. So luckily I'm old, so it's okay. Jennifer, you still there? Yeah, you are. You ladies have any questions while we're waiting? Still got about 4 minutes before everybody gets here, but I'm just signing in early in case anybody had any questions. Hello, Jennifer. I have another friend named Jen. You look just like her, at least in that little photo up there. It's like I have my friend from Florida in here.
There's a lot of us.
Yeah, yeah, pretty common name. Were y'all able to do the homework and everything? Anybody have any problems with homework stuff?
My only issue was the due dates were changing on me.
Okay, I did change them like I think I did it last night or yesterday afternoon or something, namely because partly because I'm just trying to be a little bit more kind to you guys, but also because I know the scenario is, you guys are not a big deal because you took an online class, but all my other classes have been having an online class even though they signed up for a face-to-face, but because of my surgery. So I'm sorry about the due dates changing like that. Hopefully they were for the better though.
I was just confused. I was in the middle of one and then it like disappeared on me.
Oh,
And I
that's
was like,
crazy.
and
Now that could be what happens when I adjust them while somebody's in it. I didn't know that, but I should take that into consideration from now on.
so, but it was okay. I think I had finished it or mostly finished it. So
Is this your first physics class, Jennifer?
yes.
Are you scared?
And it's been a minute since my last science class altogether. Like I've been doing the maths, but science.
Hmm,
So I'm trying to catch up. It's
gotcha.
been about 20 years since my last science class.
So you're a non-traditional student then.
Yes.
Yeah. Yeah, you guys normally do really well, so don't worry too much about that. I tell my students, my non-traditional students usually kick butt. Uh,
Well, I found the extra help in the book, and so that's exciting to me. I'm very
oh,
happy
good.
about that. So
Good deal. Make sure you remember you still have access to my cell phone number, so you can always text me, especially if you text me if you send me an email and I don't respond in a timely fashion, definitely text me. But sometimes when you're just doing a problem online, you can take a photograph of it, including the answer choices if it's multiple choice, and send that to me, and that's sometimes the easiest way I can help you. But make sure you let me know. Like I said, I know you guys are doing it online. That's not the easiest way, and for our first physics class, this is definitely not the funnest, easiest thing to take. I mean, I like it. I think it's great, and I hope people have fun. But in general, I know that only
I've
weirdo.
been doing all my classes online, and so going into the class for the lab was an adjustment.
Gotcha.
I enjoy online. I find it a little bit better for me.
Good, good.
Yeah.
I've tried a couple of them since becoming a teacher. Oh God, I do not like taking online classes. I guess I'm sort of not a little bit not disciplined enough, which is weird because I'm so disciplined. I teach myself stuff all the time. Constantly working through books from grad school and stuff like that. But for some reason, when I'm taking an online course, it's just I drift off like a snowflake. We're finally getting some people in. We got 5 in now. Roxanne, did you have any questions, or Hannah, or any of you other folks that popped in? I say Caden came in and Jonathan. I ended up having to push class back again today. I wasn't going to. I was actually going to try to come in, but between my shoulders still killing me, I've taken on some kind of sickness or something. I've got a real bad headache, real bad sneezing. My neck's hurting where my lymph nodes are swollen. My throat's hurting where I don't know what happened. I'm pretty sure it's cancer. That's just my go-to because I'm a hypochondriac and everything's cancer or Alzheimer's with me. I shouldn't make jokes like that, obviously, but it's the only way I can giggle as opposed to cry. A little like Chandler. My wife's always getting on me for that. And it's really bad because we just had a lot of people close to us that died from cancer. So it seems feckless of me to do that, and I shouldn't be. Hmm. Oh, we're up to 7 people in. Ooh, Infinity's here. I was teaching today at 1, and my new baby Chihuahua started barking his head off for no reason. And then I hollered at him, told him to be quiet, and he looked like I'd really hurt him, and he walked off like, and I felt bad. He's a goober. Caden, you got some head shaking going on there. You have any questions?
No, I'm just looking at a to-do list I made a week ago and haven't even checked anything off yet.
The best thing is to have a list, though. Once you get the list, you're 90% done. Feel free, you guys. We got actually it's time up now, but anybody have any questions about any homework problems or anything like that? I'm going to try to remember to ask y'all at the beginning of every class, but I do forget. So feel free to stop me if I jump in and start steamrolling you guys. All right. Well, it looks like we've got essentially everybody in. Looks like we got maybe 12 students in here. It's 2 minutes past time to start, so I guess we should start. When we last met, uh, I had gotten into deriving the kinematic equations for you, but the kinematic equations that I derived, well, I'd come short of one. So I'm gonna copy a page and put it in front of this one so I can finish up what I was doing with that. Specifically, there's a equation that relates to the squares of velocities to the acceleration and the position. So I'm going to start off with doing that just so you'll know where that equation came from. So let me go ahead and share my screen with you guys. Feel free to stop me if you have any questions. Again, if you remember a question with your homework, ideally you want to wait till I'm finished with a given, problem I'm solving or with a given uh, thing I'm teaching. But then after that, go ahead and ask me because I don't want you missing your chance to ask questions. And then I want to remind everybody that you can always text me. I Texting's mostly for people when they send emails and I don't respond in time, but sometimes you just need to get something quick from me, and you'd be surprised how often I can answer that way. So I just want you guys to know that that's an option. All right, so we had derived a bunch of equations. Uh, I'm going to relist those equations in a second before I start to solve the problems. But one that I had was x. Whoa, Nelly, I'm writing with the wrong thing. One that I had come up with was x is equal to 1/2 at squared plus v0t plus x0. Hopefully, y'all remember me doing that. Another one we had come up with, again, both of these were for constant acceleration. V is equal to V0 plus AT. So this is for A equals a constant. And this one's for A equals a constant. And what I explained to you guys is that sometimes you want to be able to find the distance, but you don't necessarily have time. In other words, you don't have the time parameter, how long the object's actually moving. So you would like to have an equation that maybe gets distance traveled or final velocities without using time. So what I'm going to do is I'm going to take the second equation, solve for t, and what you'll see is t is equal to v minus v0 over a. Hopefully everybody can see the algebra I did to get there. And by the way, this is a super skill. This is like, this puts you in the upper echelons when you can solve your algebraic expressions algebraically instead of numerically. So you definitely want to do that as much as possible. And the more problems you can solve like that, the better off you'll be as well, because you can not only get an answer for a problem, you get an answer for an infinity of problems. So that's something that's helpful. And it just makes you more mature as a student of engineering or science. So now what I'm going to do is I'm going to take that t and I'm going to substitute it into the first equation, and I'm going to go ahead and pull the x0 over to the other side. So instead of having just x on the left, I'm going to have x minus x0, and then I'm going to say that's 1/2 a, and then I'm going to write v minus v0 over a. That's going to be squared. Plus, I also have the V0t term, so I have to put V minus V0 over A there as well. So now you can see that basically this is the same as the first equation. I've just substituted that expression for t, and now you see it no longer has a t. So we're going to use our rules regarding squaring binomials. In this case, for instance, I'm going to have an a squared in the bottom and an a on top. So one of those is going to cancel out. So I'll have a 1 over 2a on the bottom for the first term. And on the top will be v squared minus 2v v0 plus v0 squared. And then over here, you can see that I'm going to have plus uh, v0, I'm leaving a space in there on purpose, minus v0 squared. All that's going to be over just plain a. But notice, ideally, I'd like to have a common denominator, and all I lack for that is a 2 in the bottom. So if I multiply this by 2 and this by 2, then I've now got a common denominator. Everybody follow that? I just added those 3 2's in there. The 2 in the top and the 1 in the bottom. The 2 in the top, because remember, fraction bars are the same thing as parentheses. So you always have to distribute with them and pay close attention to signs being carried throughout and stuff like that. So ultimately, I get v squared minus 2v v0 plus v0 squared plus 2v v0 minus 2v0 squared. All of that is just going to be over 2a. And now you can see that 2v0 negative is canceling out with negative positive 2v0. And you can also see that this guy right here, negative 2v0 squared plus v0 squared, is just going to give me negative v0 squared. So I ultimately will have v squared minus v0 squared over 2a. Now I can go ahead and solve for it, and I'll actually take a couple steps. First off, I'm going to write v squared minus v0 squared on one side, and then I'm going to write 2a times x minus x0 on the other side. And now I'm going to add v0 squared to both sides, and that'll be the final form. So I get v squared is equal to v0 squared plus 2 times a times x minus x0. So that's another equation that's valid for a equals a constant. So it's another one of our kinematic equations, in other words. Anybody have any questions on that? Okay, so this derivation where I started with a equals a constant, and then I set that equal to dv over dt, and then I integrated, and I got, v of t is equal to v0 plus at. Then I set the v of t equal to dx dt, integrated again, and ended up getting this x equals 1/2 at squared plus v0t plus x0. All of that is what we call a derivation for the kinematic equations that we use, and those kinematic equations are specifically for v being, or excuse me, for the acceleration being a constant. If the acceleration is not a constant, but the acceleration doesn't change hugely, that's an approximation for the right answer. But in general, you're really only supposed to use it for a equals a constant. So one of the other facets of this course is that sometimes you're given a case where the acceleration is not a constant. And in fact, you could be given the acceleration as a function of time, and you'll need to know how to go through that exact same process that I did last time and then finished up today to come up with new equations. So that's what this next example is about. It says if the acceleration of an object is given by a of t equals 3.0 t cubed plus 2.0 t minus 4.0, and the velocity is 1.4 meters per second at t equals 0.0 seconds, and the position is 1.0 meters at t equals 0.0 seconds, then answer the following questions. That's a really bad looking S. Question A, what are the units of 3.0, 2.0, and negative 4.0 in the acceleration? That's something when I see a of t equals 3t cubed plus 2t minus 4.0, that's immediately the first thing I start to look for is what kind of units would that thing have in order for it to actually work. And you guys want to get into that mode where you always look at something and see if the units work right, because a lot of times you can save yourself a buttload of problems by just looking at it unit wise. So what I'll tell you is that unit wise, A of t has units of meters per second every second. And I always want you to say it as meters per second every second or meters per second per second. That's fine as well. But mathematically, that is exactly equivalent to meters per second squared. And I don't mind you writing that, but I really think what I've found over the years is I think students better understand the difference between acceleration and velocity when they read the units of acceleration as meters per second, because it literally means how much the velocity is changing in meters per second every second. So that's why I'm doing that. All right, so there's the A of t. That would be the left-hand side of that. And then the 3.0, with some units times t cubed has to have those same units, which is meters per second per second. Okay. So that tells you the 3.0 must have units of meters per second to the fifth power. Now that sounds really weird, but that's the nature of it. If you're going to be multiplying by t cubed, and remember t is measured in seconds as well, then when I multiply 3.0 times seconds times seconds times seconds, out better pop meters per second squared. So that's how you do that. Now I'm going to do the same thing with the 2.0. So I'm going to say 2.0, and this is all part A. 2.0 units t. That's got to equal meters per second every second. So hopefully, again, you can see that 2.0 must be in meters per second cubed. Does that make sense to everyone? And let's let you guys try the 4.0. Anybody come up with an answer on that one? Hopefully you did, and hopefully it's that. Does that make sense? There's going to be a lot of times in this course, both in this semester as well as next semester, where we'll have functions that we just make up like that. And we, as students of math, are not used to having units in our equations. So part of us taking physics is about figuring out how do the units work out in these equations. So I think it's worthwhile for us to do that. And just remember, the units can always keep us from making careless mistakes. They can often allow us to figure out an equation that we don't know or we don't remember. And quite often it becomes the correct one. So that's part A. Anybody have any units on, have any questions on that part A? All right, so here goes part B. This is the big boy part, okay? So the big boy part, what we're taking is, and I'm going to just drop all the point zeros and all the units now because it's too much junk to write. So I'm just going to write 3t cubed plus 2t minus 4. And I'm going to leave a little space, and then I'm going to set that equal to dv dt. And I'll leave a little space there as well. Now, in order to solve this, what I'm going to do is multiply both sides by dt. So just so you'll see it, I'll put a dt in black and I'll put a dt in black here. And then I integrate both sides. Okay. Now, there's a couple ways you can do this. You can actually integrate and use range of integration and therefore not have any constants. Or you can do this where it's indefinite integrals and you'll get a constant in this case on both sides, but you know how you can flip around those constants and add them to make a new constant and all that sort of stuff. So in this first part, or the second part B, I'm going to do it that way where I'm using the constants of integration from indefinite integrals. So when I go ahead and integrate this, I think you all will agree that the integral of 3t cubed would be 3/4 t to the fourth. The integral of 2t becomes t squared. So that's just going to become t squared because I integrate t and that becomes t squared divided by 2, and the 2 disappears with that one. And then minus 4 becomes minus 4t. And then that was an indefinite integral, so I'll say plus C1. On the right-hand side, I'm just using the fundamental theorem of calculus. So I'll remind you guys that this part right here is the fundamental theorem of calculus. You know, there's no reason for Newton to have discovered that. Nature didn't owe us that, but lo and behold, the technique that we use to find the instantaneous rate of change or the slope of a graph happens to be the exact opposite operation of finding the area under the curve. And that's the fundamental theorem of calculus, that integrals undo derivatives and derivatives undo integrals. So when I take the integral of a derivative, I just get back the original function. So I'm going to write this as v. I'm going to write it in the appropriate color as v of t plus c2. Now, if you've been doing much with indefinite integrals, you know we often combine those constants. If you've been taking differential equations yet, you'll know that you do it a lot more. So I'm going to do that. I'm going to solve for v of t. I'm going to say v of t is equal to 3/4 t to the fourth plus t squared minus 4t. And I have plus C1, but I'm going to pull the C2 over there. So that'd be plus C1 minus C2. So I'm just going to say plus C. In other words, I made a new constant. The constant, which was originally C1 minus C2, is now just called C, and that's okay. Now I'm going to make use of this little tidbit, which says the velocity is 1.4 meters per second at t equals 0.0 seconds. So what I do with that is this. I say 1.4 is equal to 3/4 of 0 to the fourth plus 0 squared minus 4 times 0 plus c, and that tells us that c is equal to 1.4, and technically it also tells us the units of c are going to be 1.4 meters per second. Does everybody follow what I did there? Anybody have any questions about that? So I can now finally say that v of t is equal to 3/4 t to the fourth plus t squared minus 4t plus 1.4, like that. And that's going to be the answer to part B. So that's the one I did by indefinite integrals. In doing part C, just so you'll see how it's done, I'm going to go ahead and do that with definite integrals. So you'll hopefully see that as well. So here goes part C. Part C, I'm going to use 3/4 t to the fourth plus t squared minus 4t plus 1.4 space is equal to, now that was v of t, and we know v of t is a derivative of the position with respect to time, so that's going to be dx over dt. Now, just like I did before, I'm going to multiply both sides by dt. This time I'm doing it in red just to juice it up a bit. And I'm going to integrate in red as well. Only I'm going to integrate on the left-hand side from t equals 0 to just plain t, which generally mathematicians do not like, okay? You're not supposed to integrate to the variable that you're integrating with respect to, but we do it all the time in physics because we're crackheads. Not literally, but well, some of us are, I'm sure. So not this guy. I'm too boring. All right. So this is going to be from x of 0 to x of t. Because notice when you're integrating dx here because the dt's are like they're canceling out. So by doing that, what we're going to get is, it's like somebody else came in. Hold on a second. So what we're going to get is back to blue, 3/4, and now I'm going to say t to the fourth minus 0 to the fourth. In other words, that's me evaluating it first at t and then second at t equals 0. Plus, now I'm going to say t squared. Whoa. I didn't integrate. Hold on a second. I got a little excited and jumped ahead of myself. Sorry about that, everybody. All right. Let me draw the carriage back a little bit here. So I'll integrate this side without the range of integration. That'll be the cleanest way. So when I integrate 3/4 t to the fourth, that becomes 3/20 of t to the fifth. So that's 3/20 t to the fifth plus 1/3 t cubed minus 2t squared plus 1.4 t, and that's evaluated from 0 to t, and that's equal to x evaluated from x of 0 to x of t, like that. So just putting those little vertical bars, that tells you, hey, I'm getting ready to do the range of integration part. So hopefully that becomes clear to you guys. So now I'm going to do 3/20, and I have to evaluate it at t. That gives me t to the fifth. Now I have to evaluate it at 0. That gives me 0 to the fifth. And then plus 1/3. I have to evaluate it again at t. So that's t cubed minus 0 cubed. And then minus 2, evaluated at t. So that's t squared minus 0 squared. And then plus 1.4, now t minus 0. So that's the whole left-hand side. The right-hand side, on the other hand, is going to give me x of t minus x at 0, which this is where we use the position is 1.0 meters at t equals 0 seconds. So this tells you this is 1.0 meters. Does that make sense to everyone? So now I can just solve for x of t, which is really the function, the functional value of the position as a function of time, or it's also called the trajectory. So I'm going to do that, and what I'll get is x of t is equal to 3/20 t to the fifth plus 1/3 t cubed minus 2t squared plus 1.4 t plus 1.0 meters. Notice I've moved the minus x of 0 to the left, and that's it. That's the whole expression. You'll see when you start taking your practice tests, which I'll probably make them available tomorrow. When you start taking your practice tests, you'll see that there's problems like this for chapters 1 and 2 in the practice test bank. So it's something that it's a skill set you're supposed to have. So anybody have any questions on that? I'd recommend trying to make up your own A of T functions and do them. Of course, what you're seeing here is you had A is dVdt, and you can use that to solve for V of t. Then you have V of t is equal to dx dt, which you can use that to solve for x of t. What you see is that's a basically twice integrating. And every time you integrate, if you don't have a range of integration, you have to add a integration constant. Another way of looking at that is in reality, what we have is a second order differential equation. We have something that I have to integrate twice to get the result I want. And for each order of integration, you need one initial value. Now, the typical thing is the problem will give you the velocity at t equals 0, and it'll give you the position at t equals 0. That's, 9 out of 10 problems, how they'll word them, but they don't have to be. We could give you, for instance, the velocity at t equals 1.5 seconds and the velocity at t equals 7.5 seconds. Or we could give you the position at t equals 0.3 seconds and t equal 984 seconds. As long as I got two initial conditions, and the word initial needs to be in quotation marks because it doesn't have to be initial. That's what corresponds to t equals 0. But that's the point, is there's no way of doing this without those two pieces of data that I underlined in red and black. Anybody have any questions on that? You might also think about it this way. If you ever pull up to a stop sign, for instance, I often drive through Pungo and stuff on my way to work from North Carolina, and there's a road, an intersection that I come to. It's called what is it? Dang it, don't really matter anyways. But it's like Road to Heavens or some weird name like that or whatever. And I pull there. When I look down the road, if I just took a snapshot of a car down the road from me at that intersection, I couldn't look at that photograph and decide whether I should pull out or not. In fact, what I would need is either a video of it or at least two photographs, and I'd know which one was first, which one was second, and how much time was between them. Then I could reason it as well. And that's the nature of it. You're solving for X, how far away the car is, say, as a function of time. And the differential equation that dictates that is a second order differential equation. So you have to have two facts. That's why you can't just pull up to an intersection, take a quick look, and dart out, or else you'll end up getting in a wreck. So that's another way of thinking about it. And I like to tie those things, especially when you start taking it in differential equations and stuff like that. Tie that to the reality as much as you can so it doesn't look so abstract. Hopefully that'll help. Any questions on this before we move along? Notice I did part B and part C two entirely different ways, and I did that on purpose. I did it specifically so you'd see the indefinite integral way and then so you'd see the definite integral way. Hopefully that was helpful, not distracting. All right. So here's the equations that we derived for the special case of accelerations equal a constant, which, by the way, I did label next to them. There's another equation your book gives you, but I didn't give you and I didn't derive it. It's actually pretty easy to derive if you actually realize that if you make a graph of velocity versus time on a velocity versus time graph, what part of the graph gives you the acceleration? Does anybody recall that? I'll give you a hint. The answer may be in one of these equations that you see numbered right now. So you make a velocity on the vertical axis, time on the horizontal axis. What aspect of that graph could help us figure out what the acceleration is? I think you said it, Jennifer, but I didn't hear you.
Slope.
Exactly. You see A is equal to dV/dt, right? So yes, that's exactly right. It's the slope. So if you actually make a plot of an acceleration being a constant, it's going to be a linear equation. And then you can see, oh, wow, the average velocity is just add two velocities and divide it by two. So that's why equation 9 is there. And it doesn't have to be the velocity at t equals 0 and then the velocity at 1 second or anything. It literally is just two different values of velocity. As long as the acceleration is a constant, you can use that equation. And sometimes that equation makes a lot of algebra go away. So I never used it too much when I took this course. Like I think I maybe used it one time in the whole 3 semester sequence. But since I became a teacher, I was like, man, this thing really comes in handy and I can avoid a lot of algebra by doing it. So hopefully that'll help you guys. So let's look. Example, an airplane must reach a speed of 30.0 meters per second in order to take off. I don't know why I put a hyphen in there. I didn't have to because it was two separate words. But anyways, I was originally thinking of a different part of speech when I put it in there. The supposed to be airplane, even though the L makes it look like Gurplane, the good old Gurplane. So the airplane also can accelerate at 1.90 meters per second every second. A, how long must the runway be? Okay. So in other words, later I'm going to ask a little bit more about this without the runway. I mean, with it, but it's just not shown right now. That's why I have a part A there. So let's work on part A. So I'm looking for a way to find how long must the runway be. Can anybody tell me which of the variables in your kinematic equation is most closely related to how long a runway would be? Would that be, for instance, velocity or time or acceleration or x? What?
Would it be X?
Yes, it would be X. That's part of the thing is making things that you know in everyday life makes perfect sense, is try to make them into the words that you're used to. So yeah, when I say how long must the runway be, there's a way you could interpret that to mean how long am I going to have to ride down the runway, in which case it'd be time, but in this case we're clearly talking about X. So what we're looking for part A is X. So what I'll do is I'll put X is equal to question mark. Now, a lot of physics, when you first start, like y'all are doing right now, especially if you haven't had a physics class before, it's one, learning these equations, which luckily I'm going to give you an equation sheet so you don't have to memorize them. But if you work enough of them, yeah, you're probably going to memorize them anyways. But that's one of the things you do. And two, you have to know what all the symbols mean. So you have to know, for instance, that velocity is displacement divided by time, often has units of meters per second, so on and so forth. If I have a velocity with a subscript 0 or a subscript I, that means initial. So that's part of the learning game too. And then thirdly, a lot of physics problems are just solved by you looking at the variables that you're given, which are given to you in the problem, and the variables that are implied by the problem. So they don't necessarily give you them. You just got to make sense that that's the reasonable thing to assume. And then finding an equation that relates the variables that you have to the one that you want. That's a lot of physics can be done that way. Okay. So right now, what we know is we're looking for X because Infinity was good enough to tell us that the length of the runway was probably X. Now, the cool thing is, remember, the X0 is your initial position, and that's just a matter of where you put your origin of your coordinates. So you can always, always, always let X0 equal 0. You can just force that. Okay. So I'm just going to force that just to make my life a little easier. Another thing, it says an airplane must reach a speed of 30 meters per second in order to take off. The airplane also can accelerate at 1.90 meters per second. How long must the runway be? So there's something that's implied here that you might not realize. I think once I tell it to you in this case, because it's not so obvious, but in this case, I think once I tell it to you, you'll understand. Would y'all agree that the initial velocity for this plane we should assume to be 0? Yeah, that otherwise you would be solving for a shorter runway, right? If you started off at some speed greater than 0, then you've got a head start, and therefore you wouldn't have to have the runway that long. So yeah, we're going to assume that V0 is equal to 0. We don't know anything about time. We do know that the acceleration will be 1.90 meters per second every second. And we know that the final velocity, notice that's the velocity that it has to reach in order for it to go airborne. The final velocity must in fact equal 30.0 meters per second. So I've now written down the variables that were either given to me outright or implied. And I've written the variable that I want to know. Now I'm just going to look up in equations 1 through 9 and see if there's any equation that relates those variables. Does anybody see an equation that relates those variables? And feel free to just blurt it out. I'm going to go ahead and put up the chat if I can ever get it to come up now. It's being a butthole. There it is. Okay, gotcha. So now I got the chat window up in case anybody types it instead of saying it. Anybody see an equation that relates the variables that we want to the variables that we have?
Equation 7.
7 does, except it includes the time. So what would happen there is you could use that and solve for time and then use the time in something else to get the distance. So it would work, but it'd be a 2-step problem instead of a 1-step problem.
Oh, then it'd be, yeah, 8.
8, excellent. That's exactly the one I expected you to choose. And don't feel bad. Like if you happen to go to turn in a homework or look at someone else's homework or something like that, and you see that they're solving a problem with a different equation than you did, that doesn't mean they're wrong. That doesn't mean you're wrong. A lot of physics problems can be solved a lot of different ways. So yeah, I'm going to use equation 8. So from 8, what I'm going to say is v squared is equal to v0 squared plus 2a x minus x0. So one way you can do this is I'm wanting to solve for x. So I could just solve that symbolically for x. And that's a much more mature way of doing it. But sometimes you're just trying to get it over with quick. So I'm going to do it the normal way that most students do it. But I would say try to make that your goal and see if you can solve these equations algebraically eventually, let's say by the end of the semester. So I know my final velocity is going to be 30. So I'll put 30.0 meters per second. That's going to be squared is equal to 0 squared plus 2 times 1.90. That's meters per second every second. And then times x minus 0. Okay. So what we can do is we can say 900 meters squared per second squared is equal to, now you might notice 2 times 1.9 would be 3.8. So that's 3.80 meters per second times x. So now I can solve for x by dividing 900 meters squared per second squared by 3.80 meters per second. Notice I've got 2 seconds, so they'll cancel out, but I've only got 1 meter, so all I'm left with is the 1 meter on top, but that's what I expect the units of x to be. So if I do 900 divided by, and here's where I'm going to make sure I didn't make a careless arithmetic mistake. I'm actually going to say divided by parentheses 2 times 1.90, just in case I did something stupid, and that's 236.8. So that's the answer. Notice I had 3 sig figs with everything. So this 8 is an extra digit, and that's the way we carry them. Just carry it with an underline. That way you can always keep track of where it was supposed to be rounded, and you can do the rounding at the end. Any questions on that?
I have a question.
Go for
Sorry
it.
for my voice.
No problem.
But say we were solving this variably. So because we know that the initial of x is 0 and the initial velocity is 0, we could cancel those out and then we're left with v squared plus 2ax. So once we divide 2a, okay.
Yep.
I was
It's
gonna
even
ask,
easier that way, right? Yeah.
yeah,
Sometimes you can sort of do halfway. So you actually substituted in the two zeros and that made it easier. If you didn't do it that way, I'll just show you what it would have looked like. I would say v squared minus v0 squared is equal to 2a times x minus x0. And then I would say v squared minus v0 squared over 2a is equal to x minus x0. And then I'd say x is equal to v squared minus v0 squared over 2a plus x0. So that's the way you could do it if you really wanted to do it algebraically. And that's without, substituting in the easy zeros.
yeah, I did that first.
Yeah, it's good practice. And like I said, it makes you much stronger at your algebra and it keeps your skill set up. I would recommend you guys trying to do, a physics problem every day. Between that and doing things like that, that'll definitely keep your skill set up. All right. Any questions on that? So part B, I could ask you, how long does it take to reach the 30 meters per second? So let's do that. I'm going to say this is now part B. How long will the acceleration to 30.0 meters per second take? So that's another question we could ask. Now what I'm looking for is, again, I have an acceleration, I have an initial velocity, I have a final velocity, and I want to know time. Anybody see an equation that might be helpful for me there? One through nine.
6.
Yeah, that's a good one. And that's probably the easiest one to use as well. So yes, V is equal to V0 plus AT. So now what I'm going to do is I'll say T. This time I'm actually solving it as opposed to putting in the numbers first, just to let you see that. So T is going to be V minus V0 over A. That final velocity, of course, is 30.0 meters per second minus 0. And then all that's going to be divided by 1.90 meters per second every second. So when I divide meters per second by meters per second every second, that leaves me a second. So I'm going to do 30 divided by 1.9. That gives me 15.79 seconds. And of course, I'm using 3 sig figs, so that 9's an extra. Any questions on that? We could actually add another part to that too, C. Let's try this. What would A have to be if X was 230.0 meters? So that's another sort of tough question. So let's regroup and let's say, okay, maybe there's been a bad storm. We just lost 6.4 meters or 6.8 meters of our runway. What kind of aircraft can we actually allow? Well, what we do is say, well, what's the acceleration of your aircraft? And then they tell us, and then we say, okay, well, then you can take off. Or we tell them, no, well, you better get started, speed up before you get to the runway because you need to have an initial velocity. So what I'm going to do now is I'm going to look for A given X and X0. Anybody have an idea what equation you'd want to use? Infinity, you look like you might have got excited and had it there for a second.
I was thinking, would we be able to use equation 8 again?
Yep, absolutely. So yeah, we could use equation 8 again, which I was lucky enough to have sort of solved, but I didn't really solve it for the variable we want. What we want is a. So I'm going to say v squared is equal to v0 squared plus 2ax minus x0. And here's what where I'm going to do what Infinity suggested is I'm going to make use of some of the data that's already 0. So that'll make it kind of nice. In other words, x0 is 0 and v0 is 0. So now I have v squared is equal to 2ax. So a is just v squared over 2x. So that's going to be 30.0 meters per second squared divided by 2 times 230.0 meters. And if I do that math, it looks like I'm going to have 900 divided by parentheses 2 times 230 close parentheses, and that gives me 1.957. So see all the different things you could do with this one problem. You can, force yourself to find a whole bunch of stuff. Now, I only had 3 sig figs in one of those, so that 7's got to have an underline under it. But anybody have any questions with that one? All right. So we've done some of the kinematic equation applications, and I highly, highly, highly recommend you go to week 2 and week 3 of 2, of course, as well. But week 2 has a lot of kinematic problems listed in the optional videos, so I would definitely recommend you watch those. And then the bare minimum in a physics class is, unless the instructor explicitly tells you that some certain problem or some certain subsection of the book is not going to be covered, then other than that, you need to know how to do every example that the book has. If like I said, if the instructor says one subsection is not included, then you can skip the examples in there. Or if they specifically say this example is not something that I'd ask you to do, then you can skip it that way. But the bare minimum you guys should be able to do even before you really start your homework or practice test is make sure you could, in principle, close your book after writing down example, let's say 3-1 or something, write down the problem for 3-1 example, and then solve it with the book closed. If you can't do that, you're not understanding it well enough and you need a little bit more practice. So that's sort of one of the, I wouldn't say the holy grail, but that's at least a really fancy cup that you want to make sure you master. Okay. All right. So we've done a lot of the kinematic stuff. I've told you about making sure you want to make sure you look at all those videos on my YouTube channel as well as the examples in the book. Between those examples, that you should have more than enough to be able to complete all the homework stuff related to chapter 2. And this, the nature of physics is it's a comprehensive subject. So when you get to chapter 9, you're gonna literally still be doing stuff from chapter 1, chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, chapter 7, and chapter 8. So just keep that in mind. Nothing is like optional. There's no little part where you can say, well, I didn't understand that. I'll just leave that. No. That's not going to work. Okay. It's going to come back and bite you in the butt. So anyways, keep that up. And we're going to go on to now what Galileo did. So Galileo, and by the way, this is like within a day or two of the anniversary of him being brought before the Inquisition. So basically, Galileo had read about a guy named Hans Lippershey who had created a spyglass, and he wanted to make one himself. So he made one, and then he made it even better. And not only that, him and another guy named Thomas Harriot, who was the physician slash scientist for the area known as the Lost Colony in Manio. That person also did the same thing as Galileo did, also at the same time. And it looks like from his notes, he actually beat Galileo to the punch, but he was in the Americas, the New World. So no one found out about it for a long time after Galileo had said it. But either way, the cool thing is both Galileo and Thomas Harriot turned their telescope to the heavens. And Thomas Harriot mostly focused on the moon. Galileo did focus on the moon, but he also went further. He saw what he called the Medicean moons. The Medici family were very powerful and very wealthy. And if you want to shake somebody down for some cash, you name some stuff after them that's good, and that'll do it. So that's what he did. He was definitely a money hoe, if you will. He was definitely out for making as much money as he could. So he named those four Medicean moons, which we now call the Galilean moons, Io, Europa, Ganymede, and Callisto. He named them the Medicean moons, and it was a really big deal because at the time we were using Aristotelian physics, and Aristotelian physics, the physics of Aristotle, basically had been in place for on the order of 1,000 years. So it was sort of a big deal. Not only that, the entire structure of Christianity had adopted Aristotelian physics, and all the scriptures had been interpreted in light of Aristotelian physics. So if you go screwing with that, you could really mess up some stuff. So it was a really, really big deal. But what Aristotelian physics said was that there was, four elements, five if you count the heavens: earth, wind, fire, water. Mila Jovovich is the other one. She's the fifth element. You and maybe three other people might have seen that movie with Bruce Willis and Mila Jovovich, but she was called the fifth element because she was the quintessence, which is the heavens. Okay. And the other elements, earth was earth-like stuff, air, which is, the wind and stuff, water, and now I forgot them all. Fire. Fire's the other one. So you might not think that's much of science, but Aristotle was a brilliant logician, and if he had appropriate initial conditions that he took as facts, then his logic was impeccable. But the problem was he made a lot of assumptions that he thought were obvious that we've since determined were not obvious. So one of his obvious things was the heavens are perfect, ergo they cannot change. Because if they change, they would change from perfection to not perfect, or they would change from perfect to not perfect. Either way was unacceptable. So that couldn't happen. He also included change, meaning not speeding up or slowing down. So that meant all the planets had to orbit the Earth in the perfect shape, which was a sphere, or maybe a circle if you reduce it to 2 dimensions. And they couldn't speed up or slow down because obviously that would be the lack of perfection. So that was all problematic. There were 2 types of motion. There was violent motion and natural motion. The natural motion occurred when things were trying to get to their appropriate place. So, for instance, things made of earth, their natural place is the center of the earth. So, no force is required to pick up a rock, which is made of earth, and you just let it go. It's going to fall towards the center of the earth. Yes, they did know that the earth was spherical. Aristotle knew that. In fact, Aristotle had done a pretty crappy calculation of it, and had he had Christopher Columbus had access to the better number and knew it was better, he probably wouldn't even planned his trip over here, specifically because the technology might not have allowed him to make it that far unless there was a new world. So Aristotle had predicted the Earth was about 40% smaller, so that would have been kind of problematic. But you can see with the earth motion, something made out of earth is going to naturally fall towards the center of the earth. That's natural motion. If you try to take that rock and move it along the floor, then it's violent motion, and you have to constantly give it a force to maintain that motion because its natural state, everything's natural state, was sitting still. He could even describe, for instance, how smoke wafted up from a fire. If you set a fire, you probably set it using tree limbs, which if you look closely at the wood in a tree, you see it's partly earth and it's partly air. You'll see little air pockets and holes and stuff like that in it. And you also see that it's on fire. The proper place for fire is like the sun up over our atmosphere. the proper place for air is up over our Earth, and the proper place for Earth is down below our atmosphere at the center. So when smoke wafted up, it wouldn't go quite as fast as you'd expect because it's partly Earth, but it also would go a little faster than just falling straight down because it's partly air and partly fire. So all that stuff sort of worked out, but it wasn't working now. So Galileo realized, hey, if I stick to this type of motion, then I can't help in any way try to understand how, for instance, the satellites of Jupiter follow it. Because in every model that existed, the Ptolemaic model, as well as the Copernican model, as well as Brahe's model, in every model that existed for the solar system, which to them was the universe, Jupiter was moving. And the idea was, if, for instance, the Earth was moving like Jupiter is around the sun, okay, then a bird sitting on a tree limb that sees a worm, if he lifted himself up to fly off of the tree limb to go down and get the worm, the Earth, which is barreling by at hundreds of meters per second, is going to leave the poor bird behind. But here we have Jupiter not doing that. So he was actually shown the instruments by which they would cut his entrails out of his scrotum. And being nearly 80 years old, he wasn't too keen on that. He didn't think that would be a fun weekend at Bernie's type of thing. So he wasn't going to do that. So he recanted instead. And luckily, his friend, who used to be a cardinal but became the Pope in the intervening period, was now the Pope. And because of that, he got off a little bit easy. They just told him he could no longer study the heavens or write anything about the heavens, and he had to recant. He had to say that the Earth doesn't move and that sort of stuff. And supposedly he, under his breath as he was walking out, said, yet it does. We actually have the transcripts. You can download them from the Vatican if you'd like, and you can read the procedure of the trials and stuff. But anyways, he didn't do that. What he did do is go home and try to understand motion, because he realized he had to understand how the satellites could follow Jupiter if he was going to understand motion at all. So what did he do? Well, he realized, when I drop this pin, say, you drop it, it's happens so fast you can't tell, does it speed up and then reach some max speed and then go at a constant speed? Does it slow down, or does it go some fixed speed instantly and stay that fixed speed till it hits ground? He couldn't understand that. He couldn't measure it either. But what he realized is that just by common ratios from trigonometry, for instance, he could make inclined planes and relate the ratio of the sides of the triangle to the ratio of the acceleration on the inclined plane versus the acceleration vertically. So he studied that. And what he discovered was that objects, when they approach an incline, they slow down. Objects, when they approach a decline, they speed up. He made the argument that if it went on a level surface, objects would go forever. He couldn't imagine that, because there's obviously going to be some difficulties with that, because obviously the Earth is not infinite. But he could imagine a scenario where he could do that, and he went to studying it and so on and so forth. And ultimately, what he was able to decide was, one, he was able to come up with the concept of velocity, and the concept of constant velocity, which we learned was a constant velocity is the kind of motion that covers the same distance in a given amount of time. So if you're talking about 1 second, it's, if you find that an object moves 3 meters every second, and you find that that's the case in every second, then you know that's a constant velocity. If you even go down to half a second, then it's going to cover a distance of 1.5 meters. Or if you go down to a tenth of a second, it's going to cover a distance of 0.3 meters. All of that's consistent with constant velocity. He also made an idea of what acceleration was and defined what constant acceleration would be. And constant acceleration, of course, is the kind of motion where the velocity changes by a fixed amount for a fixed unit of time. So for instance, if an object's accelerating at 2 meters per second every second, that means each 1 second interval, the velocity of that object will change by 2.0 meters per second. If you cut it down to half a second, then it would change by 1 meter per second. If you cut it down to a tenth of a second, then it would change to 0.2 meters per second, so on and so forth. So that's what he was able to get. And he realized that all objects tended to fall at the same rate. In other words, the acceleration of gravity was independent of the mass. And that was completely opposite of what Aristotle said. Aristotle had said that not only do objects fall, but they instantaneously fall at a rate that's directly proportional to their mass. So a 10-pound bowling ball would fall at a rate 10 times faster than a 1-pound bowling ball. Does that make sense? So with that work, he was able to determine that the acceleration A due to gravity, we're going to call G, and it has a magnitude of 9.80 meters per second every second. And of course, that's about 32.2 feet per second every second. So you can get an idea. That is pretty fast. I compared it to Usain Bolt one time. I really should update it because I know that dude from Canada beat Usain Bolt. And it might even been someone else since then. But anyways, Usain Bolt was cool and he really kicked butt. But what I discovered is Usain Bolt beats gravity for like the first 30 meters. And then from there on out, gravity owns him. So that gives you an idea. Acceleration of gravity is pretty fast. All right. So with that in mind, what I want to tell you is something else that he really understood and was able to give us was that the acceleration behaves independent of the motion. So if I tell you the object's acceleration is about 10 meters per second every second, notice that's pretty close to 9.80. Then that's going to be the acceleration if you throw the ball straight up, if you throw the ball straight down, if you drop the ball with no initial velocity, doesn't matter. It's always going to change the velocity by about 10 meters per second each second, period. So that's a big deal, and this example should show it. So it says, A, if an object is dropped from a great height above Earth and air resistance is negligible, what would the object speed be after 0.50 seconds, 1.0 seconds, 2.0 seconds, 3.0 seconds, and 4.0 seconds? And then part B, how far would it have traveled at each of those times? So that's what we're going to use. We're going to use our kinematic equations and figure that out. So for part A, what we want is what's the final velocity? So we want V equals question mark for T equals 0.5 seconds. And actually, I'm going to assume all those have at least 2 decimal places. 1.0 seconds, 2.0 seconds, 3.0 seconds, 4.0 seconds. So we want to know those velocities. And that's basically it. Does anybody know? So let's look at our equations. Can anybody tell us any equations that would actually help us with this problem? 1, 2, 3, 4, 5, 6, 7, 8, 9.
Probably 6.
Yeah, 6 would be the best one. And notice that exactly works, but I'm going to deviate a little bit from that. You're exactly right. That's exactly the equation you're using. But I want you to understand acceleration. I want you to understand what I'm meaning when I say the acceleration acts independent of the motion of the object. In this case, we just dropped the ball, so you're not going to see that much. But I want you to understand the acceleration. If I tell you the acceleration is 9.80 meters per second every second downward, then what that means is the object is going to go from some velocity to a new velocity that differs by 9.8, increasing in the downward direction. So we know at t equals 0, so v 0, which is v of 0, is equal to 0 because we dropped it. Okay. So entirely different way, but I think you'll still see that it's helpful. An entirely different way would be v of 0.50 seconds is going to be equal to 0 plus 4.90 meters per second. Okay. In other words, I'm using the fact that each second of free fall would have the velocity change by 9.8 meters per second, increasing downward. But since I only allowed it a half second, then I only get half as much acceleration. So I can write down right now that the answer is 4.90 meters per second. And that's exactly the right answer. Now, V equals V0 plus AT would also give you 0 plus 9.80 meters per second times 0.50 seconds gives you 4.90 meters per second as well. So you see the equation works, but the main thing is I wanted you to understand the motion. I wanted you to understand how that works. Can anybody possibly forget about that, the 0.5 seconds? Can anybody tell me just off the top of your head, how fast will the object be going after 1.0 seconds? I think you said it there, Jen, but you're muted again. Or you just talked really quietly.
9.8 meters
It-
per second.
Exactly. You started at 0, a whole second has elapsed, so the velocity should be 9.80 meters per second. So I'm going to say 9.80 meters per second is exactly the velocity. Again, V equals 0 plus 9.80, leaving the units off, and 1.0 gives me 9.80 meters per second down. Now remember, it is velocity, so technically we're supposed to have a magnitude and direction, so I should list that it's down as well. How about anybody have a guess what it would be for 2 seconds? Math gets kind of complicated once we get past 2 seconds, but I think y'all can probably figure out the 2-second scenario. Two times 9 is 18. 2 times 0.8 is 1.6. So I'm going to say 19.6 meters per second. Does that make sense to everyone? Notice again, equation works. How about V of 3.0 seconds? I'll give you a hint. 3 times 9.8 is 29.4. So what do you think the answer is going to be here? I should say this is 3 times 9.80. So that hopefully that helps. And then finally, the last one is V of 4.0 seconds. And that should be 0 plus 29.4. If you added 10 to that, that'd be 39.4. But then I have to subtract 0.2. So that'd be 39.2. And I'll check with my calculator, make sure I did that right. Looks like I did. Now, I don't want you to feel obligated to do this method. I want you to use whatever's helpful to you, but I do want you to understand it enough where this makes sense. The process that I just went through in the red makes sense, even though the process on the right is really, what you'd normally learn in such a course. I just wanted you to understand how acceleration works and constant acceleration specifically. So let's try part B. Anybody have any ideas about what we're going to do with B? What kind of equation should we use for B? Because it's saying how far would it have traveled at each of those times?
I had a quick question about
Yeah, go ahead.
the part A. So I thought that like velocity for gravity was like a constant rate of speed. Is that not true? Like it keeps on speeding up if you drop something?
Yeah, you probably heard of terminal velocity, and when you actually include air resistance, there is a terminal velocity, and that's supposed to be that's a set velocity that it will continue to go. But without air resistance, no, it just keeps accelerating. In principle, it could reach an infinite speed, but we discovered that once you start getting close to the speed of light, then relativity kicks in, and there's whole different rules for that. But yeah, the acceleration, often people think exactly what you did, but no, the acceleration is a constant. The velocity is not.
Oh, okay.
Okay. What makes it seem a little weird is the fact that the amount the velocity changes is constant. So it's consistently 9.80 in a second, or 32.2 feet per second every second. All right. Anybody have an idea which equation you might want to use for part B, where we're asked to find how far it travels in each of those time intervals? So if you're looking for how far, we want a variable like Infinity said earlier, like X.
7.
Yeah, 7's good. You could also use 8, but that would require you to use the results you found in the previous part. And when you're doing that kind of stuff in a graded course, you want to try to not use values you calculated unless you absolutely have to. That way, if you got the first part wrong, it doesn't take a very attentive instructor to still give you partial credit on the second part. So yeah, 8's the one. So we're going to say X is equal to 1/2 AT squared plus V0T plus X0. And like I said, you can always put the coordinate origin anywhere you want. And we did drop this, so the initial velocity is 0 as well. So I end up just getting 1/2 AT squared. What you see is something very special, and this is what Galileo discovered. The position for an object falling from rest is directly proportional to the square of the time. So what that means if you know how far it went, let's say in 1 second, then you can immediately figure out how far it went in 2 seconds, because it'd be 4 times as far, because 2 squared is 4. And if you considered 3 seconds, it'd be 9 times as far, and 4 seconds, 16 times as far, and 5 seconds, 25 times as far. So that's another way you can do this without actually doing the equations. I'm going to start off with the X of 0.5. That one's a little misleading, so I'll just do it with the equation way on that one. So X of 0.50 seconds is going to equal 1/2 times 9.80 meters per second every second times 0.50 seconds squared. So I'm going to do 0.5 times 9.8 times 0.5 times 0.5, and that gives me 1.225 meters. Okay, so that's how far it will travel in half a second. Now, if I went to 2 seconds, or let's say if I went to 1 second, 1 second is twice as big as a half a second. Do y'all agree with that? 1 second is twice as big as a half a second. So if I doubled the time, I would quadruple the distance. So if I multiplied 1.225 by 4, I'd get 4, and then 22.5 and 22.5 gives me 45. And then 45 and 45 would give me 9. So we'd expect that to be 4 times 1.225. We'd expect that to be 4.9. And what I'm going to show you is that X of 1.0 seconds is equal to 1/2 times 9.80 meters per second times 1.0 seconds squared, which is exactly 4.9 meters. So that's also consistent with 4 times 1.225. And that's because we doubled the time, and doubling the time means quadruple the distance, because X goes like T squared. So in principle, we can actually figure out what X of 2 seconds is. X of 2 seconds. 2 seconds is twice as long as 1 second. So it should go 4 times as far because again, 2 squared is 4. So it went 4.9 meters in 1 second. So it should go 4 times that, which would be 16 plus 3.6. So that would be 19.6. So what I used there was, like I said, this is 4 times x of 1.0 seconds. But notice if you also did x of 2.0 seconds, you'd get 1/2 times 9.80, leave it off the units, times 2.0 squared would give you exactly 19.6 again. So again, this part where I'm using the equation, that's the normal way you do it, but really you should be able to come up with it just like I'm doing here on the left, just by understanding how the motion is characterized. And this was a really big deal that Galileo discovered, that the distance traveled is proportional to the square of the time. So let's do x of 3. Let's see if you guys can do this one. So x of 3 seconds, 3 seconds is 3 times as long as 1 second. So how much farther should x be for 3 seconds than it is with 1 second? Anybody?
I got 44.1 meter.
Okay, 44.1. Were you using the equation, or did you use the idea that the distance is proportional to the square of the time?
Was in the equation.
Okay, that's good. So you would say 1/2 of 9.80 meters per second every second times 3.0 seconds squared, and that would be 0.5 times 9.8 times 3 squared is 9. So that gives me 44.1. But check this out. What I'm trying to see if you can do is realize, wait a second, 3 seconds is 3 times as long as 1 second. And distance is, I could write it this way, x is proportional to t squared. So if t goes up by a factor of 3, then x also goes up by a factor, not 3, but 3 squared. So at 1 second, we had 4.90 meters. Or yeah, 4.90 meters at 1 second. So I expect this one's going to be 9 times as big as that. So if I do 9 times 4, I get 36. If I do 9 times 0.9, I get 8.1. So 36 plus 8.1 is 44.1. Ain't that cool? So this is something I want you to think about. You might not be able to do it right now. It's a whole new way of thinking, and it's not necessarily, it's in some sense trivial, but it's also very much not trivial because y'all aren't seeing it, right? But that little part that I wrote out there, hopefully that helps you a little bit. All right, and then finally x of 4.0 seconds. Now in this case, 4, so x is directly proportional to t squared. Therefore, if t goes up by a factor of 4, then x will also go up by a factor of 4 squared. 4 squared is 16. 16 times 4.90 16 times 4 gives me 64, and then 16 times 0.9 gives me 1.6 times 9. That'd be 9 plus 54. So 9 plus 5.4 be 14.4. So 64 plus 14.4 would be 74, 78.4. So I'm thinking it should be 78.4, but I was doing arithmetic there. So let's check. X of 4.0 seconds is 1/2 of 9.80 meters per second times 4.0 seconds squared. So 0.5 times 9.8 times 16 gives me 78.4. Woohoo! I love it when arithmetic comes together. All right. So hopefully this little string that I'm putting this asterisk by, hopefully that's something you can think about later. It's not something that I'm going to ask you anytime soon, but it's something that you should sort of set as your goal to make sure you understand that, because then you start to understand how motion works, at least with, falling bodies. Okay. All right. The last thing we have here is a ball is thrown upward at 29.4 meters per second. Oh, our time is up. I will tell you, I've already solved this problem in my class today at noon. And in fact, I've already posted it to my YouTube channel. So you can go ahead and check it up out there if you'd like. In fact, let me tell you what it's called. So what it's called is, nope, it's not put up yet. That's why. Doop. It's going up next though. I'll probably call it acceleration due to gravity or something. Okay. So it'll be the next one up, but you can look, for instance, right now I'm looking at the one that I did put up, which is called scientific process. No, that's not it. That was 12 days ago. Heat, internal energy, temperature, and calorimetry. That's the one that was just put up 2 hours ago. But if you look at that, it actually has a label 241D01B. And why does that say D01B? I'm wondering if I think I did put the right one up, but I labeled it wrong. Let me check. Yep, that's what I did. It's the wrong problem. So it is up there. It's currently named heat, internal energy. That's what it's currently called. I'm going to change it because that's clearly a boo-boo. I copied the wrong one up on the internet. So I will fix that title, but you can find this one worked out. So you guys are free to go. It's 6:42. So class is over. I will wait for the last person to leave in case anybody has any questions. But thank you for coming, everybody. And if something comes up, oh, actually, never mind. You guys are my online class anyways. I do need everybody to email me if you happen to be attending my day labs. Okay, because I need that so I can put everybody in the lab course on Canvas and then do everything there. But I need to know exactly who it is. I know 3 of you already. It's just a matter of there might be more than 3. So if you could please email me that would be helpful. Anybody have any questions?
Yeah, for the chapter 2 homeworks, are the due dates going to be changed till this Sunday upcoming, or?
No, mainly because I think what I changed them to, I think I already changed them to like Wednesday. You could pretty much do most of what was required in that, but let me double check before I just blatantly say no. I'm gonna pull open Pearson, my lab and mastering, and see what I have there. It might be something I can do. Actually, I'm gonna go here. So I'm looking at homework chapter 2 for this class. Evidently, it's going really slow. Yeah, I've only changed that to 23, which is tomorrow. Yeah, what the heck? What I'm going to do is I'm going to change it to Saturday. Okay, that because you still have one that potentially could be due on Sunday. So I don't want to bulk you up too much, but I am going to go ahead and change this instead of the 23rd. I'm going to make it due the 27th, and the same
Okay.
thing. with the conceptual.
All right, thank you.
No problem. You're welcome. So that's been set. Anybody else have any questions? Thanks for coming, everybody.
Thank you. Have a good night.
You too.
I have
Diego,
one
or go
question
ahead. Yes, Hannah.
related just to me. I can only see the homeworks that are late. I don't see chapter 2 or any of the following homeworks.
Oh, okay. Uh, Now, when you say you're not seeing them, does that mean you're not seeing them in Canvas or you're not seeing them in MyLab and Mastering?
Both. I
Okay.
mean, I've only gone through Canvas like to click the link to get to the Pearson stuff.
Okay.
Is there easier? I've never used Pearson. Is there an easier way to get through there?
Yeah.
I'm just on a 2-week trial right now.
Gotcha. In Canvas, try this. Click on modules of to the left-hand
Mhm.
side,
Okay.
and then go to week 2, for instance. And you'll see it has chapter 2 conceptual, chapter 2 homework under homework links.
Yes. Okay. Chapter 2 homework.
Yeah, click on that. And then when you get there, you'll be in MyLab and Mastering, and there's other places where it'll show you the whole calendar of all the assignments. But that's your first place to check is in each week's module.
Okay. Yes, it shows up in the module. I just see the like the items like PHET tutorial, moving man, and all that.
Gotcha. And it doesn't
Can
put
you
the date on there in Canvas, because if I did, it screws everything up. So you have to look at it as a date in MyLab and Mastering. Sorry about that.
You're all good. I'll have to figure out how to get straight there from like a website. Can you remind me what's the difference between like the conceptual and the homework?
So the conceptual is really concepts, the stuff that you ideally would like to get out of every science course you take. Only a calculus-based physics class, they're assuming you know most of them. So what we do is we try to put in these concept homeworks, but they're only worth 5% of your course grade, so that you can still learn the concepts and get rewarded for it. But the more important stuff is the homework problems.
Homework problems. Okay.
Okay.
I have one other question, but it's about lab. About last week's lab. I don't know if you'll be able to help me out with
Yeah,
that.
you have some. No, you're taking MyLab. In fact, yeah.
Yes, I will be switching to your lab. Next week will be my first Monday that
Gotcha.
Monday of next week I'll be attending. A week from today I'll be attending your lab.
Gotcha.
And I can send you an email too to remind you about that. But for like the Excel lab, I'm having trouble with my last graph.
Okay.
Like I'm following the examples and everything, but it's not turning out how it's supposed to.
Right. If you want to, you can share your screen with me to show it to me if you'd like.
Okay, let me switch to my computer for Zoom. Join meeting.
I guess I probably don't need to record this part. I'm gonna go ahead and pause the recording.